This presentation was given at the October technical meeting for ASQ Section 904 and was intended as a brief overview of a complex subject. A starting point, if you will, in your journey of learning about regression. We're not going to go over formulas in detail as computer programs are quite capable of doing math. Instead, we'll focus on the output of the programs and what they mean. Many programs are available to do the statistics like Minitab, SAS, Sigma XL, and many more. Some questions to answer. What is correlation? What is regression? And how are regression and correlation different? So what is correlation? Well, correlation uses a formula to analyze two or more sets of numbers and returns a coefficient named R, lowercase. The sign of the number indicates whether there's a positive or inverse relationship between the two sets of numbers, say X and Y. Positive if Y increases as X increases, or negative or inverse if Y decreases as X increases. The limits of R are -1 to +1, with the limits being perfect correlation, which rarely if ever happens. And so you can think of the correlation coefficient R as being some percentage. Here is a table of confidence limits for values for R based on the sample size. Notice degrees of freedom as n-2. The second column shows the values for 95% significance for a two-tailed test, meaning you're checking to see if R is different from a random variable on either side of the mean. More on one and two-tailed tests in another tutorial. Note for that degrees of freedom of equals 30, that's a sample size of 32, you only need R to be 0.349 or about 35% to be 95% significant. However, that's not practically what we would consider a strong relationship. Regression is a statistical approach to create a useful model for predicting the behavior of some dependent variable, usually labeled Y, based on the variation in one or more independent variables, X or X's. Unlike correlation, it gives you an equation to predict Y from X or X's. One advantage of this method is it can be done using historical data. However, there are some issues with that. We don't know everything about that historical data, like how accurate were the measurements of both Y and the X's, what variables were not measured, such as ambient temperature or humidity, what to do about missing data, and the integrity of the data collection system. This can all be solved using a planned experiment, but again, that's for another tutorial. However, historical data is probably a good place to start in your understanding of your process improvement. Some terms you're going to see in regression: R squared and adjusted R squared. Note this is capital R. That's to differentiate it from the lowercase r, which indicates correlation, which measures the strength of the regression. Coefficients, those are just the numbers that we plug into the regression equation for the intercept and for the slope of each X. Analysis of variance, ANOVA, that analyzes whether the regression line slope is equal to 0. In other words, no relationship whatsoever. T-values and P-values, those are statistical measures of the significance of the coefficients for the factors. SS, or sum of squares, that's one of the bases for regression and many other statistical tests for that matter. Residuals. It sounds weird, but really residual is just the difference between actual and predicted values. And in any regression analysis, you would not only create the regression formula, but you would apply it to each X or set of X's and come up with a predicted value for Y. So then you'd want to know what the difference was between that predicted value and the actual value. How close was it? And next is collinearity. That's when two or more independent variables are correlated to each other, which means they may represent the same effect. And the last being autocorrelation. Autocorrelation is when succeeding values are dependent on preceding values. When you add multiple independent variables, R squared will be inflated, and it's not really a good measure of the strength of the regression. So R squared is adjusted based on the number of independent variables tested. Coefficients are the calculated values for the slope and intercept. Think about your linear equation you learned in geometry, where y equals mx plus b, where m is the slope and b is the y-intercept, where x equals 0. Now, in regression, since we're dealing with variables x and y, we have to add an error term. And error in this sense, this is the E that we represent here, error in this sense is just common cause variation, or some call it noise. In statistical terms, we've replaced M with beta 1 and B with beta 0. This allows us to call other coefficients for the multiple x's beta 2, beta 3, and so on. Why sum of squares? Well, sum of squares are used extensively in regression and analysis of variance. Think of the sum of squares as the top portion of this variance formula, the sum of x sub I minus x bar squared. That's the sum of squares. And these sums are additive. So that additivity makes it possible to break down the total or decompose the total variance. So look at the diagram on the right. Think of the circle here as the total sum of squares. We can separate out the sum of squares due to error, the sum of squares due to the first x and the second x, and so on and so forth. If we add all these up, they're equal to the total sum of squares. Therefore, we can calculate percentages. So if we divide this sum of squares by the error, we find out whether it's really larger or the same size as the error, just like we would in an F-test or in any other test. A good place to start your study is with correlation. Does there appear to be the relationship between the data? This case study is from the book Introduction to Linear Regression Analysis by Montgomery, Peck, and Vining. Solid rocket fuel is basically a type of rubber. With the polymerized rubber being a sustainer propellant, it burns longer, mixed with an igniter to start the burn at a very high temperature. Shear strength between the two propellants is an important quality characteristic, and it predicts the performance of the propellant inside the rocket. It's suspected that the age of the polymerized rubber influences the shear strength. Several batches were tested at varying ages to see if some prediction could be made. So if we look at the correlation matrix over here, you can see that there appears to be a strong negative correlation. See, the R is prefaced by the minus sign. So that means that as age increases, shear strength decreases. First, we can plot the data in time order so that we can rule out any time order effect on the results. We want to make sure that we're not confusing something that happens over time with the actual effect of one of the x on the y. And note that there are no specific trends in the data, but it does appear that shear strength is lower when age is higher. Next, we look at an XY plot in Excel, and there definitely appears to be a strong relationship. Regression finds the line that minimizes the distance from each data point to the best fit regression line or slope, and minimizes the distance from that line to each point. Note that Excel will put the best fit line in for you and even give you a regression formula. However, it's minus the value for error, but that's not enough. Here's a printout of the regression analysis from Sigma XL and add in for XL. At the top is a regression formula. Note that the first number is the coefficient for the beta 0, the constant, or the y-intercept, and that the second number here is the coefficient for beta 1, which is the age of propellant, or the slope. Also look at R squared and R squared adjusted. They're very close together, which they should be since there's only one variable. Um, and they are about 90%. So we could safely say that this study explains 90% of the variation in shear strength based on the variation in the age of the propellant. The third thing that's listed here is the standard root mean square error, or standard deviation. This is the standard deviation of the prediction. And so this is the accuracy of the prediction from the model. And the sigma is approximately 96, or plus or minus 1.192 psi at 95% confidence. Well, 1.96 is plus or minus is 95% confidence, but we just rounded up to 2 to make it easy on the math. Plus it means we're overestimating just slightly. The next thing you see are the coefficients, the standard error of the coefficient, the t-value, and the p-value. And remember here we said that if the p-value was 0.05 or less, that we would reject a null hypothesis and say that there was some significant difference due to this variable. Now we also show the variance inflation factor. That doesn't really apply when you only have one factor, and we'll explain that a little bit more later. The next thing down this is the analysis of variance for the model. Remember, what we're trying to answer here is the slope of the regression line equal to 0? And this p-value gives us the exact probability that the slope of that line equals 0. And notice our probability is 0.0000. So we have to reject that hypothesis and say that with very high confidence that the slope of the regression line is not 0. And the last thing down here is the Durbin-Watson test for autocorrelation. There's a statistic and then a value for positive and negative correlation. So autocorrelation, DW gives a value between 0 and 4. 2, perfect 2 means there's none, no autocorrelation. Values between 0 and 2 indicate negative correlation, and a value between 2 and 4 indicates positive correlation. However, we're not done yet. We need to check the assumptions about the residuals. Remember that residual is the difference between the actual value of y and the predicted value of y. In this case, y being our shear strength in PSI. So the first assumption is that residuals should be normally distributed. So we have a histogram, and then we also have a normal probability plot. Now the histogram doesn't look very normal, but that's largely because we didn't have very many samples. And you know, for a histogram to look normal, you really have to have 30 or 32 or absolutely really 50 samples to look really normal, if it is normal. However, the normal probability plot does show, because it has the 95% confidence bands, it does show that this is pretty normal. There's one point here that's on the limit. That's some indication of non-normality, but not large enough to be important. So the second thing about normal distribution of the residuals is that if we plot them in run order, there should be no specific pattern. So if we look at this, there really is no specific pattern to this data in run order. Likewise, there should be no real pattern in the predicted values versus the shear strength. So at this point, we'd say this is a pretty good regression study. So what does this mean from a practical standpoint? Well, we have our formula. We have our standard error. Let's say shear strength must be 1,800 min. So with 95% confidence, we'd want 1,800 to equal our regression formula minus 192. Why minus 192? Because we always want to make sure that that standard error, we're at the outer limit of that standard error at our low dimension, so that we are always going to be within our specification. So rewriting that, we come up with an equation that looks like this, and without going through the math, approximately 17 weeks is the maximum age to meet shear strength. Now there's a warning here. Since the maximum time studied was 25 weeks, it's unwise and can be dangerous to try to extrapolate beyond that range. So if we wanted to know what shear strength was at 30 weeks, we really have no idea, because shear strength may level out, become a straight line, or it may drop off rapidly, exponentially. We just don't know because we haven't tested out that way. So always be careful that you don't try to apply your regression formula outside the area that you studied. And then on the other hand of that, make sure that the area that you're studying is the area that you're interested in. Multiple linear regression involves more than one independent variable tested against a dependent variable. Now we have a coefficient for each x variable. This becomes a little more complex, as a single two-dimensional plot cannot represent this relationship. The cardinal rule of regression is that the simplest model is the best. So now if we have multiple x's, they may not all be significant. And the insignificant ones, the ones that don't pass the 0.05 test, or whatever test that you put it at, 0.06, that's really at the choice of the statistician. But 0.05 is kind of the gold standard. But if it doesn't pass the 0.05 test, we really need to remove it from the equation, unless it has a significant interaction, and that's something we're going to talk about in another module. And we want to do those one at a time and rerun our regression until we finally have the simplest model that has the best adjusted R-square that explains our relationship. And again, adjusted R-squared is the one that you're looking at now. It's not uncommon to do multiple linear regression and have R-squared be almost 100%. And then look at adjusted R-squared and it's 65%. That's because you've basically filled up that total sum of squares, and when you divide it out, it's huge. So we have to adjust it for the number of factors. So, and we also must test for collinearity. That's where two or more variables are representing the same relationship to the independent variable, or they're correlated to each other. So in multiple linear, here's another case from the Introduction to Linear Regression Analysis. This has to do with a soft drink vendor and the delivery to vending machines. The engineer in this case thinks that two things are most important: the number of cases delivered to each machine and the distance from the truck to the machine itself. And that's ×2, because the delivery person has to take empties back to the truck as well, and may have to make several trips to fill the machine. So what do? Well, we plot all the data and we do a correlation study. And looking at the correlation study, we have very high values. They're all positive: 0.96, 0.89, 0.82. This says that delivery time has a positive relationship with the number of cases and the distance, and also that the distance has some relationship to the number of cases. That may or may not be true, but we'll see. Now, when we look down here, we plot all the data in time order, or in the order that it was gathered. And if you look at this bottom plot, that's the distance. And note that it looks very similar to the upper plots, but it's offset. That's going to be important, and we'll see how that works out in the analysis. Note that R-squared adjusted is approximately 96%. Does this number have to be that large to indicate a successful study? We'll talk about that in a minute. The root mean square error, 3.25, which means we should be able to predict within plus or minus 6.5 minutes delivery time. I don't know whether that's good enough, but the engineer surely knows. And we look down at the parameter estimates, and both the number of cases and the distance are extremely significant, much lower than 0.05, less than 0.001, so significant at 99% plus. Then the next is this VIF. That's the variance inflation factor. They are not red, and there's a reason for that. If it's less than 5 to 10, that indicates there's a lack of collinearity. So even though our initial study, a correlation study, showed that these two might be related to each other, they don't interfere with each other in the prediction equation. So they're not correlated enough to really interfere with each other in this equation. In the analysis of variance for the model, remember we're trying to determine whether the slope of the regression line is 0. P-value says the probability of that is almost nothing. So we have to reject that idea and say that the slope actually is non-zero. And the last thing we have down here is we have a significant value for positive autocorrelation. Think about it this way, that positive autocorrelation means that the delivery they made prior has some influence on the delivery they made, the next delivery that they made. And if we looked at the data, we could see that, particularly on elements 5 and 10. And if you printed this off, you can see that. Both of those are about the same amount, but one is 60% longer. And it's 60% longer because the previous delivery had a very, very long distance from the truck to the vending machine. The question is, does that make enough difference that we have to account for it? And the answer is practically no. Looking at the residual analysis, we have a very normal residual pattern. So this appears to be a good model. So in summary, you're going to do a regression study. First of all, make sure you got good data. Do a correlation and run order plots to find out if there's any relationships or patterns in the data. Run your regression analysis, whatever software you use. Look for t-values near or greater than 2. That'll result in significant p-values. If it's multiple linear regression, be sure and look at adjusted R-squared to test how strong the relationship is. And look at the diagnostics. Are the residuals normally distributed? Is there a pattern in the run order of residuals? In another tutorial, we may talk about some problems that you might run into here and how you address them. But for right now, this is just an overview. And remember, we asked whether R-squared or R-squared adjusted, did it have to be 80 or 90%? Think about it. If you identify a third or a half of the variation, and you can make a good prediction for a third and a half of it, you've learned quite a bit. And if it's a multiple regression and there are factors that you found are insignificant, then you've learned that you don't have to spend money to control them. So it's not a failure if your regression study turns out to not have a very high R-squared. You always learn something. And finally, some good quotes to think about before we close. All these are by George Box. He wrote the book on statistics for experimenters. Was head of the statistics department at Wisconsin. A prolific author and very good statistician. Remember that every model is an approximation. We're force-fitting the data into a mathematical model. That doesn't mean that nature intended it that way. That just means that we've found a way to explain it. The model is hypothetical. It's a conjecture that may or may not summarize or explain important features of the data. And a good chestnut that a lot of people use, all models are wrong, some models are useful. So even though we force fit the data into a model, it may be wrong, but it might be useful. And we found 2 instances here where the model was useful in predicting some information. Thank you, and we'll see you again.